Works.
Yeah.
Thank you, everyone.
So let's start.
Moine, and this is joint work with Chargueraud and Francois Pottier about the specification and verification of a transient stack. A transient data structure is a bundle of an ephemeral interface. For example, you can concat two ephemeral strings by appending the second one in the first one. A persistent interface. For example, you can concat two persistent strings by producing a new persistent string without modifying the arguments. And efficient conversions between the two. So you can go from ephemeral to persistent, and from persistent to ephemeral in less than linear time. The idea dates back to Clojure, but is available in several languages such as JavaScript, Scala, C++, Haskell, or OCaml. But be warned, it is sometimes presented under the name of immutable or persistent. Sec is an OCaml library for transient sequences that is push and pop on both sides, split and concat. And sec is implemented using a tree of shared chunks. A chunk is just a fixed capacity array, and we share these chunks between different instances of a structure to ensure efficiency. But sec is a complex data structure, so we focus here on a scaled-down transient stack that is push and pop on one side and implemented using a list of shared chunks. But even if a transient stack is not very interesting by itself, this simplification preserves the two main formalization challenges of sec, which are, first, the implementation of a persistent interface using mutable and shareable chunks, and moreover, an amortized time complexity analysis, because these chunks will need to be copied from time to time. Our equipment for such a task is separation logic, since it is well suited to analyze imperative programs, extended with time credits for the time complexity analysis, and we use interactive theorem proving because we use a non-ownership approach of chunks, which is non-trivial. All of this is available within Chargueraud's CFML, so we are ready to go. The main contribution is the first, to the best of our knowledge, the specification and verification of a transient data structure. It rests on the verification of runtime ownership tests based on unique identifiers. We moreover present an example of a non-trivial monotonic shared state. Also, we equip our transient stack with efficient iterators, which can coexist on the same stack, so we handle the logical invalidation when needed. Finally, we verify the amortized time complexity of all our operations. In number, we have 250 lines of OCaml, which needed 1,400 lines of code specifications and 1,800 lines of code proof. Now, let me show you first the interface of our stacks, then insights of the implementation, and finally, key parts of the proof. So, first, a type for ephemeral stacks. So you can create an ephemeral stack, push in an ephemeral stack, or pop in a non-empty ephemeral stack. Then we have a type for persistent stacks. So you can create a persistent stack, push in a persistent stack, or pop in a non-empty persistent stack. But crucially, we provide constant time conversions between the two. So you can go from ephemeral to persistent and from persistent to ephemeral in constant time. But how is this possible? At a high level, a transient stack is just a linked list of fixed capacity arrays. More precisely, here is an ephemeral stack which consists of a list of chunks. The head chunk here is of capacity equals k equals 4, with 3 taken slots and 1 empty slot. We have then a tail of full chunks. And as I said, some of these chunks may be shared. So a chunk in the tail of an ephemeral stack is either uniquely owned or may be shared with other structures. Typically, a chunk will be shared with a persistent stack, because a persistent stack always shares all of these chunks, Moreover, the head chunk of a persistent stack consists of a view of a prefix of a shared chunk for efficiency reasons. But now, let me show you some specifications for these operations. First of all, a specification for ephemeral push in CFML. Here is a simplified specification in a purely ephemeral world. This is standard. If I want to push X in E, and I know that E represents any stack of model L, then ePush will modify E to represent any stack of model X counts with L. Notice that in the precondition we require 7 time credits, so a constant number of time credits, so ePush is specified as a constant time operation. But as I said earlier, the ephemeral stack depends on a shared memory. Therefore, we annotate a representation predicate with a memory and assert its existence on the heap using a shared heap predicate. Notice that ePush does not modify the shared memory. It is the same in the precondition and in the post-condition. Therefore, we use a CFML notation to specify ePush as invariant in the shared memory. Now, let's see the specification for persistent push. If I want to, it is first a bit harder to read because the representation predicate for P stacks lives in prop. Indeed, the knowledge about a persistent structure is itself persistent. So, if I want to push X in P, and I know that P represents a P stack of model L, then P push will return a new persistent stack P prime, which represents X close with L, so we push X in the model. Notice that we require here a higher but still constant number of time credit to account for a possible copy of a chunk. But as I said earlier, a persistent stack depends on a shared memory. Therefore, we annotate a representation predicate with the memory. But notice that ppush will modify this memory. So we existentially quantify over a new memory M prime here, which extends the first one. And this extend predicate is important because it specifies that ppush modified monotonically the shared memory. Indeed, all representation predicates are monotonic with respect to extend. So if I know that a P stack represents a stack in some memory M, and if I know that M prime extends M, then P still represents the same stack in the extended memory M prime. And because almost all operations are monotonic, we introduced a new CFML notation, mono here. So we specify ppush as monotonic in M, which is just syntax sugar for this big specification. Now let's see conversions. For example, we can go from ephemeral to persistent. So if I have an stack E, which represents an stack of model L, then ephemeral to persistent will destruct this ephemeral stack and produce a new persistent stack P, which represents the same stack. Here we require 2 times credit, so we are constant number of time credit, so we are in constant time, and we are monotonic in the shared memory. Why? Because ephemeral to persistent will share all of the uniquely owned chunks of E. In the other direction, we can go from persistent to ephemeral. So if we have a persistent stack P, we can use persistent to ephemeral on P and obtain a new ephemeral stack, E, which represents the same stack, ephemeral. We require in the operation condition a higher but still constant number of time credits to account for some copies, but we are invariant in the shared memory. Now let's see some insight on the implementation. Indeed, ephemeral stack use identifiers to determine whether a chunk is uniquely owned or shared, that is, in the cloud. More precisely, each ephemeral stack has a unique identifier, each chunk carries a stack identifier, and when the two match, there is unique ownership of the chunk by the ephemeral stack. This is very useful during conventions. Why? Because when going from ephemeral to persistent, we will simply generate a fresh identifier for the ephemeral stack to share all of its chunks, and in the other direction, when going from persistent to ephemeral, the new ephemeral stack will have a fresh identifier to ensure no stealing of chunks. And why is this ownership information so important? Because when trying to write in a maybe shared chunk, To avoid side effects, we have to do a copy on write. That is, we copy the chunk beforehand to ensure that the write operation will have no side effect. But, of course, we can directly write an element in a slot of an existing chunk if it is uniquely owned. Because we are the only one to use this chunk, we can always directly write in it. But we can be even more efficient. We can always write in a previously unused slot. Indeed, because the slot is unused, it will never produce a side effect even if the chunk is shared. Now let me show you how we handle this shared memory at the proof level. Indeed, the memory type is just a map from chunk addresses to their model, and the shared heap predicate is just the iterated star over the map that asserts that, in fact, on the heap, each chunk is related to its model. Then we can define the extend preorder, and the memory M' extends M if and only if the domain of M is included in the domain of M', and each chunk in M from the prefix of a chunk in M'. Now let me show you a last challenge in the proof, because we have common code operating both on uniquely owned chunks and shared chunks. And we want to analyze the code only once, so we need to introduce unifying representation predicates. For example, for chunks, we have a heap predicate for uniquely owned chunks, predicate in prop for shared chunks, and we introduce a new predicate which handles both cases. Chunk may be owned, a heap predicate, and verify the code using this predicate, and derive two set of specifications for the uniquely owned case and for the shared case. So I showed you in the introduction some iterators, so let me show you how we handle them. We provide a type for iterators, and we can iterate on both ephemeral stacks and persistent stack. Iterators have direct access to internal pointers of all stacks. So this is typically very difficult to verify using separation logic. Nevertheless, we provide three operations. We can get the current element, we can move in the iteration, we can test if we reach the end of the stack, and maybe the most important function from the verification point of view is set, which allows us to change an element in an ephemeral stack. And why is this operation interesting? It's because what happens if we try to write in a shared chunk? Because we can have multiple iterators on the same structure, writing in a shared chunk can lead to a logical imputation of other iterators. So all the details are in the paper, so check out the paper. In conclusion, we are able to prove that the Transient stack is both correct and efficient. Towards the full verification of SEC, we have first to integrate the existing formalization for bootstrapped trees, because SEC is implemented using a bootstrap tree of shared chunks and not a list of chunks. After, we have to verify the optimized representation for chart sequences made in SEC, and of course verify the many operations implemented in SEC. That's all for me. Thank you for